The cycle of water is called Earth's water cycle, and this cycle describes the movement of water molecules within the Earth's atmosphere system. So we start in the oceans and seas. Liquid water from there, and also from fresh water like lakes, ponds or rivers, evaporates. And then it rises into the atmosphere in the gas state as water vapor, and then condense to form clouds and precipitation. So that's the whole cycle that water goes through, and it's in constant movement. So water always moves from oceans to the atmosphere and then down to the Earth's surface and to into the ground. So we have those processes of water storage in oceans, evaporation, water storage in the atmosphere. Then when it falls as precipitation, it can be stored in ice and snow. Then if the temperature is above zero, the snowmelt can appear and the runoff starts. So we have snowmelt runoff to streams. Water can also infiltrate into the ground, and when it moves through the ground, there is groundwater discharge. And we can have springs, so in springs it is place where rivers start, and there are also lakes, ponds and others. And water can also flow through the surface, so then we have surface runoff. And with all these processes, hydrologists are interested. So let's start with atmospheric boundary fluxes. There are fluxes between different zones in the Earth where water vapor is transported. Then there are atmospheric dynamic processes. So clouds, forming of clouds, precipitation, then land surface atmosphere exchanges, so this evaporation and precipitation, then changes in glacial mass balance and the runoff. So if the water is stored in solid form in glaciers, on glaciers, as ice or snow, then there is also runoff when the water melts. On the seas, there is sea ice that can change, so there is sea ice mass balance and dynamics. And of course, Arctic Ocean dynamics and deep water formation. And there are many different biological dynamics and ocean food chains. And of course, there is also runoff from poorly organized lowland and flow systems, and direct groundwater discharge to the ocean. So all this discharge through networks as rivers and lakes, and also processes that happen on glaciers, in the atmosphere and in the ocean, are really important for hydrologists, because hydrologists are dealing with water. Water cycle is powered by energy from the sun, and is a continuous exchange of moisture between the ocean, the atmosphere, and the land. Here is the picture where you can see fjord, some mountains, and clouds in the atmosphere. So you can see water that is in each state, liquid in the fjord, solid on snow cover, as snow cover or glaciers, and also water vapor in the atmosphere. And water has profound consequences for Earth's climate and ecosystems. It has also capacity to store large amounts of heat and transport this heat over vast distances via ocean currents. So via ocean currents, warm waters from equator can move to higher latitudes, and for example can reach even Svalbard. So there is warmer water than it should be because of sea or ocean currents. So that's another interesting thing in case of water and its capacity of storing large amounts of heat. Ice, so water's solid phase, is less dense than liquid water, so it can float on top of liquid water, and it insulates the water underneath. So it prevents the complete freezing of bodies of water. It can be ponds, lakes, or Arctic Ocean. So if it insulates the water from above atmosphere, so low temperatures, there is insulation, so nothing's happening underneath the ice cover. So this insulating effect of ice enables the water below to sustain life through the harshest of winters. So during winter, even though it's minus 50 degrees, it can be like that, the water freezes only on top. Underneath, there is liquid water. I found some studies that calculated how much water comes from evaporation, evapotranspiration, and sublimation. So the ocean, seas, and land-based bodies of water provide nearly 90% of moisture in our atmosphere. Plants, they also breathe, let's say breathe. During this process of transpiration, they release the remaining 10% of water vapor. And this process is called evapotranspiration. So it's the water vapor that comes from plants. In addition, a very small portion of water vapor enters the atmosphere through sublimation. That's the process by which water changes directly from a solid, ice or snow, to water vapor. So in the atmosphere we have water vapor from these three processes. For clouds to form, there is one thing necessary. This thing are tiny atmospheric particles called aerosols. Around aerosols, water vapor can condense, so the water drop appears, and it condenses and forms clouds. And these clouds can produce raindrops if those small particles are growing inside the clouds. It can form raindrops or ice crystals. If they are large enough, they fall back to the Earth's surface as precipitation. And that's continuation of the water cycle. So water vapor that was in the atmosphere comes back to the Earth. And comes back, for example, as snowfall. Ice and snow affect our climate. During winter in the northern hemisphere, they can blanket up to 16% of the Earth's surface with a bright covering that reflects much of the sun's radiant energy, because there is solar radiation that comes to the Earth's surface, but it can be reflected because of albedo. That's the reflection of different materials. For example, white snow has high albedo, so it reflects back the solar radiation. And there are changes of the snow cover during different seasons, and I just downloaded some file showing how it changes from NASA. So here you can see northern hemisphere during 1 year, starting in one summer. So it starts here. And then during fall and winter, snow cover appears. And in the springtime, disappears. And stays only in high latitudes or high altitudes. So in the polar regions or in high mountains. And there are some places on Earth where the seasonal snow, where it accumulates, the snow can stay throughout the year. So its accumulation is higher than seasonal ablation. So during summer, this snow doesn't melt. It stays in this place from previous winter till next winter. And the lower topographic limit of permanent snow cover is called the snow line or equilibrium line altitude. That's the altitude above which the snow will stay from previous year. If the snow stays from previous year, the glaciers can form. Glaciers and also huge ice sheets. By the shortest definition, glacier is a mass of ice continuously moving from higher to lower ground. And here is the moment. Now it's the moment when we can check your answers. Here's the question: how many % of Earth's fresh water is stored in ice? The fresh water in lakes and rivers is only 25%. The rest is stored as ice on glaciers and ice sheets, and that's 75% of fresh water. So these answers were wrong. 75% of the world's fresh water is stored in ice, and of it, 91% is stored in Antarctic ice sheet, 8% in Greenland ice sheet, and 1% of it, 1% in mountain glaciers. And glaciers exist on every continent except Australia. On Australia there is no glaciers, but on New Zealand, just 1,600 kilometers southeast from Australia, there are mountain glaciers as well. So they appear in high mountains around the world. So water from precipitation can fall on higher latitudes and higher altitudes, and this is where the glaciers can form. And if this precipitation as snow falls lower, or it can fall as rain, it can also fall on the ground or on the glacier. If it falls on the glacier, after summer, you can see the snow from previous year in accumulation zone, which is higher part of the glacier. Below it, there is ablation zone, and this is the zone where more snow and ice is melted from previous year. But from previous year, in accumulation zone, the snow stays. So it can just grow and grow and grow in the next years. And if there is enough snow, the pressure from above forms ice, because the snow recrystallizes and it forms ice. That's how it looks. Accumulation dominant in accumulation zone, ablation dominant in ablation zone. When glacier terminates in sea, there is process of calving, so breaking of huge blocks of ice from the glacier front. And there is glacial budget, which is water balance of the glacier. If the accumulation is lower than ablation, the balance is negative, so the glacier shrinks. If accumulation is higher than ablation, the glacier grows. It can also be equal, accumulation to ablation, so the glacier will stay in the same place. Water at the surface on the glacier comes from rain or can be also melted from snow and ice, and it goes through different routes before reaching the ocean. In the accumulation area, it can percolate through the snow and firn down to ice layer. So on the top, snow melts a little bit, then water percolates through this snow layer. And it can also flow on the top of the glacier, on the glacier surface, all the way to the glacier terminus. Water can also flow through veins in englacial channels or tunnels. So there are these different veins where the water goes through inside the glacier. It can drain to the bed of the glacier, so underneath the glacier, through moulins. I will show you the moulin soon. And at the bed, the water can flow in tunnels or as a thin sheet of water, as groundwater in sediments under the ice. So water flows through the glacier when it melts. And actually, glaciers have complicated drainage systems. The meltwater flows on the surface of the glaciers, and this is where the supraglacial streams appear. Within the glacier, in tunnels, these are called englacial streams. And there can be also water at the base, so it fell through moulins and flows along or within the bed. And these streams are called subglacial. So underneath is subglacial, inside is englacial, on the top is supraglacial. And when there is tunnel, there is, of course, ice pressure from around, but there is also melting from this water flux, and of course water pressure. So the ice tries to close the tunnel, but water drains the tunnel. So in drainage systems of glaciers, we have different streams, there's supraglacial, englacial, and subglacial, and there are moulins. At the end, at the terminus of the glacier, there is proglacial outlet. So this is where the proglacial river starts to flow. From the glacier, the water goes out, and in the front flows out as a proglacial stream. I promised you to show you moulin. That's how it looks. This water from supraglacial stream falls down to the moulin and then flows through the glacier. Here are my colleagues. I recorded that. And here is the surface of the glacier. As you can see, there are many streams during summer when the snow and ice melt. There are many supraglacial streams that flow on the glacier surface. And they can fall into such moulin as here. On the top of the glacier, there are also crevasses, so cracks in the glacier surface. So these are the places where also water can drain into glacier. This is how glacier top can look like, with many crevasses. And once you walk through the glacier, there are those crevasses, and it's really dangerous. You can fall down to the crevasse. That's why you need crampons on your shoes and ice axes. So if you fall down, you have to climb up again. But actually, it's not easy during summer when there is so much water flowing through the glacier. Here is a picture of supraglacial stream. So the meltwater flows on the surface of a glacier. And moulin is a water-worn pothole formed where a surface melt stream exploits a weakness in the ice. So those moulins are cylindrical. They are usually several meters across and extend down to the glacier bed. And usually it's not easily vertical. They, for some part, are vertical, and then in series of steps, the water goes down. If you go to the place where you found the moulin during summer, and you'll go there in the late winter or spring when there is enough snow accumulation, you can go down to this moulin, but it's really risky. You have to be prepared with lots of equipment. But once you go down, during winter, the water doesn't flow usually through the glacier. So the meltwater is drained and just went out from the glacier. So this is the time when speleologists can go through the moulins and check how they look, how look the tunnels of inside the glacier. So how looks the englacial streams? If you go down the moulin, yeah, that's how it looks from below. And inside the crevasses, inside the tunnels, you can see different forms of ice. This is how the tunnel inside the glacier looks like. And when you just go down, you can just travel along these corridors, these channels. You can see it was freezing, so it was okay for me. When it was frozen, there was no water flowing. If there is water flowing, it's really hard to stay there because it's slippery. So it's really dangerous during summer, but it's less dangerous during winter to go there. And when you go there inside, you can see many different forms of glacier ice. And you can even reach the bed of the glacier. So when you see the bed, the rocks that are underneath, then you can think that you reach the bottom of the glacier. But glaciers can terminate on land, but also can terminate in the sea. When they terminate in the sea, there are those huge tunnels that go from the glacier to the sea, and during melt season there is lots of water going through these tunnels straight to the ocean. But also smaller glaciers terminate on land. And I mentioned that this is the place where the proglacial river starts. So it flows from the margin of a glacier. And those rivers are strongly affected by highly seasonal water supply from the glacier. So when there are different seasons, different parts of day, there can be more or less melted water from the glacier. So in these streams you can see different outflows during the day and also during seasons. And that's something that hydrologists are interested in. How much water, what is the discharge from the glaciers and also from different catchments, so different areas. And for that, hydrologists conduct measurements. And these measurements are for one reason, to obtain water balance. And water balance is the flow of water in and out of a system. And that's actually, a system is a catchment, so the area from which water goes out, flows out. So in general, water balance equation is precipitation equals evapotranspiration. You know what is it? Stream flow, so water discharge. And also what is the, and plus the storage in soil or the bedrock or groundwater. So it equals the water that falls down as precipitation equals evapotranspiration, stream flow, and storage. And the definitions of discharge, or called also surface runoff, refers to the horizontal water flow that occurs at the surface in rivers and streams. Water balance calculations are often performed for the catchment area. Catchment area upstream of the discharge measurement site, toward which it is often assumed to drain entirely. So this means that the hydrological boundaries of the catchment are assumed to correspond to the topographic watershed boundaries. And just to show you how the catchment looks like, I prepared this picture. So this is Fuglebecken catchment, and the boundaries are topographical. So the catchment starts in upper parts of the mountains, on the tops or on the ridge. And then from this whole area, water flows into one hydrological profile. and above this profile we have catchment. So when we say about water balance of the catchment, we have to think about whole catchment area above the hydrological profile, and we measure outflow in the hydrological profile. Surface runoff can be caused by many processes. In normal conditions, only subsurface flow contributes to stream flow when it reaches the surface. So from underneath the ground, the water infiltrates, and when it appears on the surface, you have lakes or rivers. However, it is also dependent on topography and also on soil characteristics. So they also influence the amount of discharge, how much water is flowing through river. And hydrologists measure the discharge, and discharge is volumetric flow rate of water that is transported through a given cross-sectional area. So once you go to the hydrological profile, you measure the cross-section of it, as is shown here. Below there is river bed, above there is just surface of river. And when you measure in different points, for example, in each meter or half of meter, the depth of this river, and then if you measure the velocity of water that flows, you have this distance across channel, you have water depth, and when you have the velocity, you can say about the volume of water that goes through this cross-section. So hydrologists measure velocity in the center of each compartment at 0.2 of the depth, 0.4 of the depth, and 0.8 of the depth. So at different points through the cross-section, these velocities are measured, and then outflow can be calculated. This is from we know how much water goes through the river, what is the discharge of the river. There are different methods of measurements. The most recently most popular one is the method that uses current meter. So as shown on the picture in the previous slide, the velocity area method. So in these vertical subsections in each meter, it depends on the width of the river, of course. If you have like 20 meters, you won't measure in each half of meter, but in each 1 meter or 2 meters. And then you calculate how much water goes through this river. And we do such measurements in different catchments in Hornsund Fjord on Svalbard, in the biggest island of Svalbard, in Spitsbergen. So we measure outflow from different catchments because we are interested how much fresh water goes to the sea. And we conduct measurements throughout the ablation season. During summer, when the water melts, so there is river runoff, we measure this runoff on different rivers. So you can see cross-section of the river and measurement at different points, just to get the exact amount of volume of water that flows through the cross-section. If there is bigger river, you need special suits for that, or you should use the boat to measure from the boat. And if you have different levels, because discharge changes, the level of water changes during the season. It can be higher, it can be lower. So the water discharge is high or low. And if you compare those measurements at different states of water, at different levels, for example, if the depth was 2 meters, the velocity and discharge, so the volume of water was, for example, that much. If it's deeper, there will be more water. And that's for preparation of rating curve, which is discharge versus stage. So stage of river. How deep is it in different profiles? And when you have data from air temperature, precipitation, and discharge, so flow runoff of the river, you can say something about the catchment, how it behaves, what's the functioning of this river catchment. And that's really important because now we observe, there is climate change, so we observe longer ablation seasons. So there is longer time when the water flows in these catchments. So we are interested in the behavior of the river because rivers influence the landscape and many other things. And of course, this water in the rivers comes from the precipitation and also from melting of snow. So we conduct measurements of snow cover as well. And we measure snow water equivalent, how much water will melt from the given depth of snow. We also set up time-lapse cameras just to see the changes from no snow in the catchment to full snow cover and how it changes. Just to see how the snow coverage change in, for example, Fuglebecken catchment. So what's the influence of snow onto the river runoff? Underneath, in the ground, the land in high Arctic is frozen, and it's constantly frozen, so there is permafrost. By the definition, permafrost is the frozen ground that stayed frozen for at least 2 consecutive years. So when from the previous winter the ground was below 0 degrees, and it stayed like that through whole summer, and it stayed till next winter. In next summer, it will be also, it can melt, or it can thaw, of course, but if it's frozen, there is permafrost. Above permafrost, there is thin layer. In Svalbard, it reaches up to 2.5–3 meters, the layer which thaws. So it's not frozen during summer. It freezes again in winter, but it thaws in summer. And this has many implications on the infiltration of water. So for example, if the water is underneath the ground in permafrost, there can be ground ice. But there are some places underneath where the water underground can flow, so where the ground is not frozen. So in these places there are talix. In talix, water just infiltrates and goes and can appear as spring. Recently, we observed degradation of permafrost. So once it degrades, the active layer is thicker, so it grows, it's bigger and bigger. This frozen ground, this patches of frozen ground ice, can appear on the surface as lakes. But once the active layer is thicker, those lakes also disappear. So that's something that is also measured by hydrologists. And are the lakes important in case of the Arctic? As you can see, there are many lakes in high Arctic and also in the whole Arctic. So there are many rivers, many lakes, whole ocean, different processes, and all of it are still remain quite unknown and really interesting. That's why I work as hydrologist and climatologist, to see what's the influence of climate change onto Arctic hydrology. So as expected consequence of global warming is decrease in the Earth's snow and ice cover, and that would increase the global absorption of solar radiation, because if there's no snow, the radiation won't be reflected. And this can even make the melt bigger, and it influences the disappearance of glaciers, ice sheets, and snow cover, influence the sea level. So sea level increases once the solid waters, so ice, disappears with climate change. So that's something that is really changing. The disappearance, the retreat of glaciers and ice sheets makes the sea level higher. So it's really important for those cities and towns that lay on the coastline. If the sea level is higher, it can be dangerous for people. But that's a different topic, and here I would like to finish. If you are interested, I provide further reading. If you are interested in hydrology of glaciers, you should read Glaciers and Glaciation by Ben and Evans. If you're interested in permafrost hydrology, you can find a book called Permafrost Hydrology by Ming-Ko Wu. And there are many different scientific papers on those topics. And here I provide the list of my articles. So thank you for your attention. If you have any questions, you can ask them in the chat box now.